morning, students. I hope everything is clear to you now, my voice and audio. So, welcome. We are today starting the summary of week lectures and problem solving approach, which will we see that how do we solve the numericals related to surface and volume ratio, how do we do various conversion from pico to nanometer as it was given in the assignment of week 1. We will discuss how we can classify between the natural nanomaterials, engineered nanomaterials, or incidental nanomaterials. So I have various example to discuss with you. So first we will go through the summary, and I have picked up some of the questions, some question made by me, and we will do the extensive discussion on this, and then we'll do the problems which I have designed for you. So, first question which we often get confused between what is nanoscience and nanotechnology. Nanoscience, it is another it is an extension of all the sciences like chemistry, physics, mathematics, but in the different scale of measurement. Usually, we study the bulk properties, the materials which is in micrometer, but we study the materials in the nano range. That is that is 10 to the power 9 nanometer fall into this of nanoscience, and the application of this kind of sciences into the industry, into the academics, will I will give you the definition for the nanotechnology. Okay, but is it important to like define these two, because they are most of the time is used interchangeably. So definition, it does not matter, but for your clarification I introduce these two terms. Basically we can see that there is a circular interdependent relationship, like if there is nanoscience, then there is then there is nanotechnology, and if we create some technology which is nano based, then we will look into we will look into the fundamental science, how the mechanism works. So that fall into the parameter of nanoscience. So this can be changed interchangeably. Also, when we talk about nanotechnology, it does not fall into only one of the application. It has application in agriculture, it has application in defense, it has application in academics, it has application in healthcare. It has application in healthcare. Okay, so we can see that nanotechnology runs through all the sectors. So that is why I have used the term vertical sector. It is not limited to one. It is vastly distributed in all the sectors and applications. What are nanomaterials? This is an interactive class, so I will prefer students, if you know the answer, you can also raise your hands and unmute yourself and let me know. So I will have some idea that you have this much of knowledge, and you have watched the lectures of week 1. So, Sri Pooja, can you tell me what are nanomaterials?
Good evening, ma'am.
Wait, sorry, yeah.
Am I audible?
Yes, you're audible.
So, ma'am, I think nanomaterials are particles that are over the size range from 1 nanometer to 100 nanometer,
Okay.
and um, yeah, that's the idea I got from watching the lecture.
Okay, Sripuja, you are missing one of the specific information. Is all the dimension need to be nano range, or one dimension will let you define as nanomaterials?
Sorry, ma'am.
I'm asking you. This part of your answer is correct, that it should lie into the range of 10 raised to power minus 9 meter. But I'm asking, is it important to have all the dimensions in nanoscale, or only even if the one dimension like length, breadth, height, on one of the dimension is nanometer, will it still be called nanomaterial?
I think particles having one or more dimensions less than 100 nanometer can be called as nanomaterials.
Any of the so
Sorry?
sorry. Yes, Kiran. Do you have anything?
Particles
Yes, yes.
1 to 100 nanometers is like nanomaterials. Its size range.
Yeah, you're right. So technically, my question was that see, this suppose this is a particle nanotube. This is, let's say, 10
Between
nanometer.
1 to 100 nanometers
Yeah,
is
yeah. So this is
nanomaterial.
this side is 10 nanometer. Okay, and this side is, say, let's suppose 2 micrometer. And I have one more nanotube. This is one more nanotube. This is 10
Akshita,
nanometer.
you are not audible.
Oh, sorry.
Okay.
Am I audible now?
Yeah, yes.
Sorry. So I was saying this is tube 1, this is tube 2.
Yes.
Am I audible now?
Yes, yes.
Okay. So this is 10 nanometer length, height, and this is 2 micrometer length. I have one more nanotube T2. This is 10 nanometer and this is 20 nanometer. Which of them is a nanomaterial? T1 or T2?
Um, I think T2 is a nanomaterial.
T2. Kiran, your
Yes,
answer is
T2.
T2.
T2 is nanomaterial.
Okay.
Uh,
What about C, Pooja?
I also think T2 is an nanomaterial now.
Um, so I would like to tell you, students, that both of them are nanomaterial. This was my point when I was asking the definition of nanomaterial. Even one of the dimensions, like in this case, 2 micrometer, which is one of the dimension of the nanotube, is of the 2 micrometer, but one other dimension is 10 nanometer. So this is also a nanomaterial. One, yes, Kiran, are you saying something?
yes, yes. I'm listening. Yes. How is even?
Yeah, that is why I was asking the definition. So nanomaterial, definition of nanomaterial is one of the dimension one of the dimension. There's some audio problem on my end, so kindly it will be helpful that you write your questions. Next time I will fix this audio problem. If you have
Okay.
any questions, then please write in the chat box so I will read it side by side. Apology for that audio issue. I will fix it next time, but today the class time has been started, so here it is. So the definition nanomaterial was that one of the dimension, like being length, breadth, height, diameter, any of the dimension, one of the dimension will be nanometer. It does not matter if any of the dimension is micrometer. Wait. It does not matter if any of the dimension is micrometer or not. Are you saying something, Pooja? Kiran,
No, no, no.
is your doubt
Please
clear
continue.
now?
Yes, yes.
So what is the correct answer now?
Uh,
Shri Pooja,
uh,
what is the correct answer now?
both
They're
are
both nanomaterials.
Yes, right. Okay. Now tell me, if I have a sphere of let's say 20 nanometer diameter and is also a coating of, let's
Okay.
say, 2 micrometer. Is it still a nanomaterial?
Okay. Mm,
Stick to the definition and you will know the answer.
uh, 2 micrometer and I think it is a nanomaterial.
You're not sure?
No.
It is a nanomaterial. The definition says at least one dimension should be in nanometer. So it is a nanomaterial.
Okay.
One more question. I have a lot of smaller particles.
Like one particle should be nanomaterial. Like one dimension should be nanomaterial.
At least
Okay.
one.
Okay. Okay. Okay.
I have lot of. Do you understand what are quantum dots?
Yes. Yes. Yes.
Okay. So this is suppose this is a quantum dot of gold nanoparticles. So I have drawn lot of quantum dot, and the size is around, let's say, 20 nanometer. But these quantum dot has very high surface energy. So from the distance between them is very very small now. It is like this now. And now this cluster has now become around 3 micrometer. So is it a nanomaterial now?
Yes.
Why?
Mm, uh, because it's a group of small nanoparticles only and form a cluster. I think so.
Yeah, it is not a cluster, it is an aggregate. Cluster are different types of material. Here this is
Okay.
called aggregates.
Okay. Aggregates. Okay.
So this is these were the nanoparticles. Since the surface energy is too high, they are now aggregates, but they are still nanoparticles.
Yes. Okay.
So here the first part we are clear that what are nanomaterials and you have defined it. Now question 1. What are the example of microscopic materials? And can you define what are their units?
Units for microscopic material.
What are
Um,
microscopic materials?
uh, um, Grain size and unit
Sorry,
grain size number you are talking about. Okay,
I'm
size of
asking I'm asking example of microscopic materials.
microscopic materials.
Grain
I think
size
bacteria.
is
Yeah, grain
inside
size.
the nanomaterial.
Okay.
Let me see. Let me explain grain size. So we have some irregular nanoparticle, and it is and inside the nanoparticle there are lot of defects, and it is divided into various grains randomly
Yes.
like
Yes.
this.
Okay.
This is a nanoparticle. This is grains,
Okay.
and line which differentiate between one grain to second grain is called grain boundary.
Okay.
Okay,
Yes.
and On the basis of these number of grains, we define a material to be single crystal, crystalline, polycrystalline.
Oh, yes. Okay.
Okay, so in the
Yes.
course, you must be taught what are crystalline and what is polycrystalline.
Poly definition of single crystalline.
Like, how do you differentiate? Like, what differentiates a crystalline and a polycrystalline?
Crystalline, polycrystalline. Single crystal is there like one structure is there, like one FCC structure will be there only. I think it is single crystal.
No, no,
And
no. FCC is
polycrystal.
a packing.
Uh,
How the atoms are arranged.
uh, Single crystal.
FCC is how the atoms are arranged. So,
Uh,
yeah, okay.
um,
Uh, Crystalline and polycrystalline can be differentiated on the basis of number of grains available.
yes. Okay.
Okay, if
Ah,
the grains are around 4.5, if the grains are
4.5.
around 4.5,
Okay.
then it is crystalline. Fine. Then if the grains are countless, like around more than 100, more than 20,
Okay.
okay, so then it is called polycrystalline.
Okay.
Did you
And
get?
in single,
And
in
single crystal
single.
has only one grain. There is no grain multiple. It is complete. It's a
Okay.
complete
Okay.
crystal.
Hmm.
Fine. So this is the difference. So what was my question? What is the unit for microscopic materials?
Microscopic material. Um, Micro. um, Micro. I just don't remember presently. You
Okay.
only tell.
Unit is micrometer. The answer
Micrometer,
was
yes.
already on the screen.
Ah, yes, yes.
Okay, the name says na micro.
Ah, yes.
What are the exponent for the micro? What is the exponent for the micro?
Yeah, I think so for micrometer.
Is it okay? I'm
For
going to next
minus,
page, next slide. Just to this space issue is there now. Is it minus 12? Is it
okay.
minus 15? Is it
I think
minus
minus
3?
9.
Or is it minus 6? Micrometer. Which
Uh,
of them is the correct answer?
I think minus 6. Minus 6. 10 to the power minus 6.
Correct. Then what is this stand for then? If this is micrometer, then what is does this stands for? Or do you know about this? What does it stand for? What does this stand for?
Micrometer. Um,
Any guesses? Any student can also answer. It is an interactive discussion. Other student can also answer. Okay, fine, no problem. This is millimeter. Milli. Fine. This is pico. Sorry, this is femto, and this is pico. Do you get? 1 meter is equal to 10 raised to minus 12. 1 picometer is equal to minus 12 meter. Likewise, like we said, 1 nanometer is equal to 10 raised to a minus 9 nanometer. So this is femto, femtometer. This is millimeter. This is micrometer. Are you saying something here?
No, no, no. You
Okay, okay,
continue.
okay. So
You
here
sure?
is the. So next question is prefix for the prefix nano derived from which origin? Like
Nano.
words are derived from different origin.
I think it's Greek.
Yeah, right. So Greek from the word root nanus,
Okay,
and nanus means dwarf or a little man.
okay.
Okay. So now my question will be describe characteristic unique properties of nanomaterials. What are the
I
properties of
think
nanomaterial?
nanomaterial properties.
What,
It
like
is
we
like
have studied lot of bulk materials, right? What is that
same
thing that we have to specifically study nanomaterial?
like same material when it is in macro state, its properties are different, and when it is like crushed down to nanoscale, its properties are enhanced. They increase.
Yes,
Uh, the properties vary according to the size
correct.
in nanoscale also.
Yes,
I think
absolutely right. So the picture you see is one of the thing is one of the optical properties of nanomaterials. One of the optical properties of nanomaterial on the basis of size, the light emitted by this CDS quantum dot is changing. Okay, size is reducing and okay, no, sorry, size is increasing like from 1 to 10 nanometer, and the wavelength is also increasing. Here we can see red emission, red light emission, and this is blue. This one is has a the longer wavelength. So one of the unique properties of nanomaterial is size dependent size dependent optical properties. Are you following me, everyone? But why this size dependent? From where the size dependent optical properties? I'm again repeating. If anyone has question, kindly raise your hand. Since there's an echo problem from my end, please raise your hand if you have any questions. Size dependent optical properties. This property is derived from the quantum confinement, right? In the bulk, in bulk, materials follow classical physics concepts, whereas in nano range, quantum mechanics is applicable. The energy bands like conduction and valence bands, which were which were like a continuum, continuous, like you cannot differentiate which is valence band, which is conduction band. It is like a continuum, arrays of bands in bulk. This is the feature of bulk material. In quantum, what happens? These bands are split into various energy levels, and this property makes them stand out. When the emission happens from higher to lower than the light emitted, and these energy levels, remember how much number of energy levels are there, it depend upon the size of the, fine. So that is why materials behave differently. So that is why materials behave differently in nano range. So tell me, you have a, you can see I have a slide of purple color slide. Is it, what guess, tell me, is it a ruby? Which kind of material it is? Is it a ruby? Is it copper? Is it iron? Is it gold? Or is it platinum? This is a nano material. When it is in bulk, it has a different color. But now, since it is a nano material, it is giving different color. So tell me, is it ruby? Is it copper, iron? Is it gold? Which one of this is?
No idea. No idea.
This is gold. Gold nanoparticle. Fine. When in bulk material, gold are yellow and shiny. But when it is in nano range, it is giving purple color. So,
Okay.
coming back to this question, the unique property of nanomaterial is the different optical property with the quantization of energy levels. Okay, what other property?
What other?
Everyone has heard of, sorry, everyone has heard of boron.
Yes. Yes.
Boron in the periodic table.
Yes.
Boron, is it a metal, non-metal, or semi-metallic? What is it?
Boron. Um, I think it is semi-metallic. I'm not sure.
No, it is not semi-metallic. It is non-metal.
Okay, non-metal.
So what is the physical property of non-metal?
Property of non-metal. It is non-conductor, it is non-lustrous, it is
Absolutely
non.
correct. Absolutely correct. So this property which you're saying, the property which you're saying is a bulk property. When the boron is in the bulk form, it is act as an insulator. It is not the conductor of electricity.
Okay.
Fine. But but when it is in nano form, when it is good electrical conductor, it will conduct electricity.
Okay.
It is used in claim as metal.
Okay.
Fine. So what that nano form of the boron is? Uh, Nano form of the boron is borophene. Okay. When it is in nano form, we call it borophene. Correct? Are you following me, everyone?
Like,
Pentagota?
yes. Yes.
Okay, fine. So one of the property of the nano is the electrical property. One other one was the optical property. Third property is I'm moving on to the next slide further. Surface energy. Okay. Nanoparticle have a high surface area, and that is why the surface energy is very high. Therefore, they give catalytic properties. Example, we have one conversion reaction, some form of carbon to the other form of carbon. If we use bulk platinum, this reaction will not happen. Okay. But if we use platinum nanoparticle, the reaction proceed at very spontaneous speed, spontaneously. Therefore, the catalytic properties are enhanced in nanoscale. Okay. So these are the some properties and characteristic properties of nanomaterial. Now moving on to the cluster. What are clusters? What is the definition of cluster?
Mm.
The hint is it is depend upon the number of atoms.
They have a minimum number of like stable to their surface area. They form clusters. I think stable number of atoms. They combine and form like clusters of a particular nanoparticle. I think it is like that.
The some part of your answer is right. The part which is not correct is that it is not about the nanoparticle. Nanoparticles are different in complexity and clusters are different type of materials. Clusters are known as 3 to 10 raised down minus 11 atoms. Okay, if a stable structure has atom weighing from 10 raised power minus 10 raised plus 17 atoms and it is stable, it can be called as the, there are a lot of other parameters. Fine, there are a lot of other parameters in the clusters, but here there is no elementary definition as per the others. Fine. I hope the definition is clear about the prominent difference between particles and clusters. Now question 4. So the clusters are stable, but they are not stable in other number of atoms. Suppose if I have a cluster A, it has 50 atoms, and I have cluster B, it has suppose 115 atoms. So the by virtue of its stability, it is possible that this is not stable. This sorry, A. The cluster formed by A member two atoms is not stable. So such numbers we call magic numbers. Okay, but how does it explain the different theory which we have, which I will discuss in the next slide? So the magic number of particle definition is the magic number of particles is based on which model? Like this atom is stable, other atom is not stable. Which model define this magic number concept? Anybody? The answer? Answer is Jallium model. It is different from atomistic model. Jallium model does like you everyone knows that in when we do quantization we have 1s, 2s, 2p6 like this. The num the electrons are all filled in. Electrons are filled in 1s2. 8 electrons are filled in the second shell. Like this. This is atomistic level. Yeah. But in Jallium model, this atoms, this is cluster. It is 1s2, 1p6. This is atom and this is cluster. The electron filling is different in cluster. The electron filling is different in cluster. Wait. The electron filling is different in cluster and dif and as different from atom. It is 1s2. There is no 1p6 is not there. It is 2s2. Here we have 1p6, 1d10. So electron filling in the cluster is different and this is based on the Jallium model. Is that clear now? The Jallium model is based on the free electron metal, fine, and involve very basal functions and other boundary conditions. That is why the electron filling is different. I hope everyone is clear. So the magic number of a particular element is based on which model? It is J-Liam model. Now moving on to the next question. What is the magic number for aluminium? Everybody knows of gold. It has magic number least, the least count, the least stable structures, least with least number of atom. The stable cluster is 55. AU 55. What is the magic number for aluminium? The magic number for aluminium is Al 13. Okay, it has 39 free electrons. There is a minus sign over here, and there is active charge, active minus charge, and if we include this minus charge also, then in the J-Liam model we will say it has 40 free electrons. On your screen, there are various examples like of water, hydrogen bonded cluster of 5 water molecules. Okay, so this is H2O 5. Even molecules form cluster, not only atoms but molecules also form cluster. Here is the, okay, tell me, is this is C60 palladium, is it a natural nanomaterial or engineered nanomaterial? The classification which you have studied.
It's an engineered nanomaterial.
Yeah, right. So this is engineered nanomaterial, but also a cluster. Okay, it is a nanomaterial because the dimensions are in nano, but the number of atom which is involved is 660. There are also stable cluster like C72, C74. Fine. So this is also a part of clusters. Here is also another example, carbon Q of C8H8. These are molecule based clusters. Another cluster is carbon dodecahedral with structure C20H20. Here are the example of the different close pack structure like FCC structure, hexagonal structure, and isooctahedral structure with the cluster of the all the it is the example of Al13 only, but different packing. Okay, all three are stable, but they will differ in the performance. One may have more electrochemical property, one may not have a good catalytic property. So the clusters are there, but with different properties. Fine. So what is one of the properties of this cluster Al13? One of the properties of Al13 is, we see aluminium is a metal. In bulk, it get oxidized, right? It forms Al2O3. But when it is in cluster form, when aluminium is in cluster form, it prevents oxidation. That is one of the characteristic properties of clusters. Another example, copper. If you left copper in open, it will get tarnished, right? It loses its shine because of the oxidation. But there are various clusters like C20, Cu20, Cu40, Cu58, and one more is Cu92, right? These are the clusters of copper prevents oxidation. Fine. Are you getting what is the purpose of clusters and how they are different from the nanomaterials and bulk material as well? The most stark difference between them is the quantization of energy levels, how the electrons are supposedly filled. Okay, the azimuthal quantum number it has. The L is different. In the atomistic model, if you have third shell, okay, if you have third shell, so it need so in the atomic string model, the N should be greater or equal to L. But when we talk clusters based on Galium model, it is not necessary. It can be uh, like this does not follow anymore. Fine, it can be greater than N also. Like here we see na, where was it is like this is here N is 1, but L is 3 in clusters. Whereas in atomistic 2p6 like we have here, suppose N is 2, here N is 2, not suppose N is 2. So L is 2 or it can be less than 2, like if we have 2s2 only. Fine. So this is a stark difference between both clusters and nanomaterials. Moving on to the next slides. Explain types of synthesis approach. There are various approaches that we use to synthesize nanomaterial. It is not easy to synthesize nanomaterial if we want a particular unique property. So we have to follow different approaches as per our requirement. So anybody tell me what are the different like synthesis approach we follow? We follow to synthesize nanomaterial.
I think it's top to bottom and bottom to top.
Yeah, right, Shashwat and correct. Top to bottom, like we say top down. The word is top down, and one is bottom up approach. These two are we take. So this is the example. Like here, in I have to explain you. So in top to bottom happens that we have a larger particle, and through various stress and strain, we break down those particles into nanoparticles. So we say it is a top down approach, like electro spinning. This is one of the example, like ball milling. Fine. These are the example of top down approach. Here in this, like I will now, I'm first explain ball milling, then electrospinning. Here we take some salts of bulk range, like obviously micrometer range. They are precursors like sodium chloride or maybe sodium carbonate. Then we ground it, like we do, like what we do in mortar pestle. We ground it very vigorously, and for a longer time. It can be like if we are using machine, so the precursors should be ground for at least 10 to 20 hours if you are using a machine. So long time it takes. And then in heat conditions, our material nanomaterial is formed. There should be proper not at every temperature nanomaterial form. It may be possible that 500 degree of nanomaterial is not forming, but at 1000 degree it is forming. It's fine. So heat condition is also matter. So this is from the micrometer precursors we have derived to nanomaterial product. What happened in electrospinning? We prepare a bulk solution and stir it vigorously. Then it is put it into a machine from which thread-like particles are, like, this solution is put into the machine, and this at the end of this machine has a injection, and from that injection thread-like particles are derived. Fine, these particles are very minute. Length is long but diameter is very small. So we have got a nanomaterial type soul. And then we heat it and we get a very fine powder. From bulk solution we have got fine powder. So this is a top down approach. What is bottom up? One more example of bottom up approach. Yes, like now we will move on to the bottom approach. I was thinking of explaining other problems also, but let's move on to bottom up approach because we have other problems to solve. Bottom up approach. Examples of bottom up approaches: sol gel. Yeah, right. Chemical precipitation. Obviously, correct. The scientific name, like scientific name for the chemical precipitation method is micro emulsion. That is chemical precipitation. Okay, what happens? The difference between electrospinning and the sol gel is, here everything is same. The bulk solution is there, but it is not injected. The sol is made to dry. The sol is made to dry. Whatever solvent it has, whatever solution solvent it has in the bulk solution, it get dry. Okay, once it get dry, then we heat it and then we get a nanoparticles. So when we dry, it is not bulk anymore. It has gone into the nano range. So that is why the sol gel is in the bottom up approach. Okay. In microemulsion also, it is a different approach. We mix two different types of solvents in two different beakers. Fine, and then we put in one. Suppose like in beaker one, do you have a space? No. In beaker one, I put some organic solvent. In beaker B, I put some aqueous solvent and my salts. When you mix them two in a particular ratio, A into B in particular ratio, then precipitate is formed. That is chemical precipitation. So these are the different types of synthesis approach which we take when you want to synthesize nanomaterials. Next question. What are the imperfections in a ball milling grinding? Every synthesis process has disadvantages and advantages. What are the disadvantages if we choose ball milling, the top down approach, as our synthesis process? Anyone? Right. Crystals and surface imperfections are there. We don't know what planes have been formed. Like in crystal, the planes are there. We don't know what planes are formed. We don't know that all the particles have uniformly ground well and every particle has got equal or optimum time. Okay, it is a very random process. The grinding is very random. So there are always chance of crystal and surface imperfection. Whereas in these soul gel or microemulsion, you get very precise and very faceted structures. What I mean by faceted structures, like in ball milling, you will not get like if you have a cube, it has different planes, 101, 001. In ball milling, you will get all these planes. But if you synthesize my microemulsion soul gel op, appropriately, then you will get only single plane. Hope maybe 100, 02, only single plane. Fine. So if this happens, then if you want to study a electrochemical property, and your electrochemical property is enhanced at when your sample is exposed to 002 plane, then it is good, then the performance is enhanced. But if you go by this and your performance is not enhanced, the electrochemical performance is not enhanced. Fine. So these are the things you have to keep in mind before deciding upon the approach you want to before deciding on the synthesis approach you want to carry forward. Fine. So this question number 7 is done. Now moving on to the question number 8. What do you mean by polydisperse? There was one of the properties of nanomaterial, monodispersity. What do you mean by polydisperse? Polydisperse means that the particles are of different sizes. It is not dispersed properly. Fine. We have the particles of different sizes in our sample, and there it can be like for 2 nanometer we have 100 particles, for a 5 nanometer we have 500 particles, like this. So the our sample is polydisperse, it is not monodisperse. Okay, it has formed local sections of our of particular size of material. Equation for polydispersity of polymers, this you will search for yourself, and you will realize that there is why the equation for polydispersity of polymers uh, was there. See, polymers are long chain of repeating units, like repeating unit of carbon chain, repeating unit of carbonyl chains, fine chains. So that repeating unit is not fixed. It can has 10 repeating units. It can has 15 repeating unit. So the molecular weight of each chain is different from the other. Fine. So if we have this kind of situation, then it is called polydispersity of polymers. Okay. Then to find out what is the actual weight, or like what is the average weight, or what is the actual weight of the polymer, which has so different kind of molecular weight of different chains of different molecular weight. So we need equation for this, and this you will check for yourself. Fine. Now moving on to the few examples of types of nanomaterials. Examples of natural nanomaterials. Okay. So the first example is bone. Bone bone has our bone, human bones have natural material. You know, bones are very strong yet very fragile and brittle. Okay. it gives supports to our body. But but this is because of the natural nanomaterial which is present. The chemical formula for the bone is, first let me tell you the formula of bone. This is a bone, human bone. Calcium phosphate hydroxide. It's called hydroxy. I think if I'm right, if it's spelled like this. Can you see this part and this part? It has very smaller structures, fibrous like structure. If you see, can you see it properly? Then it has very fibrous like structures. So this fibrous like structure is 300 nanometer long and 1.5 nanometer thick. Can you imagine? Your bones have nanoparticle which has 3 nanometer long and thickness is 1.5 nanometer thick. This is the this is that these are the nanoparticle fibrous like particles just giving strength to your bone. So this is a natural nanomaterial. Gecko's feet. This is a reptile, gecko, and it is known for its sticky feet. Okay, if you it can climb walls because of the it's because it has a very stickness on its feet. Fine. What does what is the specialty which it feet give from where this special feature come in this? When we zoomed, when we these are the do you know what are these images called? These are called SEM images. You will learn in the upcoming lectures how to study and characterize the material. How do a scientist came to know that this is the structure of the gecko's feet? How does a scientist came to know that the bone has this kind of structures? So these are SEM images. Fine. So when we zoomed it also had a standing arrays of structures. Like these are the arrays, the lines which is formed. It is called arrays. So this it is 75 micrometer if you see the scale in length, but the thickness is very small. The thickness is in the nano range. So this is a property. These tiny little crystals, they let gecko's toe make contact with the surface and then it is able to climb. Fine. Lotus effect. This is also example of natural nanomaterial. Has anybody has witnessed a lotus effect? Can you see the picture and explain me what I'm trying to explain in this picture A? Yes. Do you know what is the specialty when a droplet of water falls on the lotus leaf? Anyone? So the lotus effect refers to the water repellency and self-cleaning. The lotus is known for the fact that when we drop a water droplet on its surface, then it repels water and water does not stay over its leaf and it falls down. Fine. And in this way, when it falls down, it does also act as a self-cleaning because there is no it does not let dust also sit over the leaf because it washes away. So it means that is water repellent and self cleaning. This is a speciality of lotus. And saw the micrographs. This is SEM micrograph, like SEM image, SEM micrograph. It was like this structure. Has like grains like structure. When we zoomed into this feature as well, then we got to know about lot of fibrous like particle, and then we see it has a rod like particles, little aggregated rods. These are nanomaterials but aggregated. So this feature helps to be act as a water repellent and self cleaning agent. Using this lotus effect, there are now a lot of textiles, like fabrics have been developed for defense purposes, because there is no water on the high altitudes. Okay, it is a very cold temperature, freezing temperature. So to maintain the hygienic conditions, to so the fabrics have been designed on this type of concept, on this type of technology. Fine. So we take inspiration from natural material and then we engineered in our daily life. Fine. Another example is the uh, wings of butterfly. Now I have shown you a lot of examples. Can you tell me why this butterfly has a blue color? We have seen optical properties of nanomaterial. Now anybody can tell. Explain this property. We can see that uh, when we zoom, this is a special butterfly. Okay, which gives blue, which imparts blue color. It is called Menelaus blue morpho. It is its scientific name. Okay, so when we zoom it into the its feathers, her feathers, we see long tube-like structures, and then we go for higher magnification. This was in micrometer range. This gap is 1 micrometer, but this cross sectional and these smaller particles are in nano range. Okay, so because this is in nano range and we know that there is a size dependency of the optical properties, this imparts blue color to the blue morpho, right? So here we studied the examples of natural materials like bone, gecko's feet, lotus effect, blue color, and that is why, nature has we it's very difficult to make blue color. It was very difficult to make blue LEDs. The LEDs which were first discovered was red. Blue need much more smaller size. Okay, much more smaller size of nanoparticles. The humans made it later. It was difficult for us as humans to make blue LEDs, but it was not a challenge for nature to make it. So that is why blue color is very rare. So this is one of the unique example how nature acts. Next question. What are the electron microscopes? What are electron microscope and their types? I was telling you these are the micrographs. Electron, do you know what are electron microscope? Then I will discuss it further. Anyone? You can write your answer in chat box if you don't want to unmute yourself. What are electron micrographs? This is an interactive discussion, so I request you to interact. What are electron microscopes? One of the hint is that these images are taken from electron microscopes. Do you understand these images? Okay. If you want to see a bacteria, we use light microscopes, right? Like in college or in school, you have done some experiments to see bacteria, or onion peel experiment you have must have been done. Yeah, right. As the name suggests, the light microscope use light as source to see objects. But electron microscopes use high strong beam of electrons to see the electrons. Right? There are different type of electron microscope. Scanning electron microscope, uh, transmission electron microscope. These microscope help us to see the things at nanoscale, and these are the images for the scanning electron microscope which I was talking about. There is a why was there is a need to move from light to electron microscope. We can see things under light microscope, so why we need to develop such high sophisticated, high maintenance electron microscope? Anybody? The answer is magnification. The answer is resolution. See, our eyes cannot see the cells of the onion peels because our eyes cannot be magnified to that level. That is why we need these light microscope. But there are n number of things which we require to see the things at nanoscale. So we need much more high magnification, much more powerful tool to go into that nano range. And that is why electron microscope came. We are able to see things in electron microscope because the wavelength of electron lies in the nano range. The wavelength electron lies in the nano range. We are able to see the onion peel, the small protozoa, bacteria in light microscope because their size is compatible to the wavelength of the light which we are using. So it depends upon the magnification. Fine. And other one was the resolution. The light microscope. See here, if you would have used, I will show the difference between light, the pictorial images of difference between light and electron microscope images in the next class, and you will be amazed that if this picture is taken on the light microscope, you won't be able to see it as clearly as this structure. You won't able to see these detailed structure. So resolution, this is called resolution. Electron microscope gave far much better resolution than the light microscope. Can you tell what is the resolution of our human eye? Like, you can see two things apart till what metric? The resolution means you can differentiate between two adjacent things. So what is the resolution of human eye? It is around 8 micrometer. We're able to differentiate between things up to 8 micrometer. Whereas electron microscope, very powerful, are able to differentiate between even up to 5 nanometer. So this is a so these electron microscopes are powerful tool. Can human eyes be magnified naturally? Is it yes or a no? No. If you're able to, you can magnify some little bit, but not as much as magnified as electron microscope. The electron microscope is able to magnify a micrometer image up to 50,000 x. And if it is TEM, transmission electron microscope, it can able to magnify image up to 100. This is a unit for magnification which we use, x. This is kilo, 50,000 x, 1 lakh x. So here are some tools that we are able to see these amazing features of nanomaterials. Next question. What was the takeaway message for Feynman's iconic talk? I'm talking about Richard Feynman's talk on there is plenty of room at the bottom. In the video lectures, we discussed in the video lecture we discussed three features of this talk. What were those? The hint, I'm giving you the hint. You can write your answers in the chat box. How to write, how to read, how to solve the storage. Mr. The scientist Richard Feynman discussed 3 points in his iconic talk. Can you explain how did he explain how to write in the nanoscale? Anyone? Richard Feynman told that we can able to write things on the head of the pin. You know, small pin which we put in the panel board. We can able to write those pin on that pin. A whole book we can write on it. Fine. Using fib fib technique, focused ion beam, which I will explain in this section. We can able to read these things using reverse microscopes. Okay, how we will able to read it? First, we should know we can write it. So there is a machine. If we want to type letter E, then it will create a cavity of E on the substrate. Fine. In very small nano range, because the tip is also around 0.1 nanometer. The tip of that fib technique is in 0.1 nanometer. And to read it, we have to deposit some material at an angle, so it is able to fill not the cavity but the area near around it. So the E part is very clearly visible now. and if we put a microscope, then we can read what has been written. So this was the takeaway message, that how the phenomenon explain to write and read at the nano range. And how did we solve the storage problems? He told that if we are able to write anything, like if you want to write anything, if you want to save anything in the, able to save or write things in the form of 0 and 1 bits, which we call in some coding format, then instead of writing long sentence, it can be written in 0 and binary form, like well, it's much more number, not 0, it can be 2 3 4, but some kind of code language. That, and using this concept, using this concept using this concept, the floppy disks have now been replaced by our SD cards in the phone. Using this, the bulk music system has been replaced by iPods by Apple, because they have solved the storage problem. These are the features. But Mr. Feynman was such a great scientist that he was able to predict even these three. He was able to predict these technologies which were very very far away, which was not even started when he was giving the speech in 1959. These technologies were not even existed. It was very at rudimentary level. So the foresight which he had is remarkable. So the next question: who was the first scientist? Sorry, who was the first scientist to use the term nanotechnology? This this is the second question which you will look for, and then previous question you have to look for the equation for the polydispersity of polymers, right? Now I will explain you the fifth mechanism. Does anybody understand what is the fifth mechanism? How does focused ion beam works? No, no problem. The fifth stand for focused ion beam, and when it is combined with scanning electron microscope, then it is known as FEAB SEM. Why is it lacking? Here we see in the A part, this is a substrate which I was talking about. This is a tip. There is a ion beam fall onto the solid material, and we get various backscattered secondary electrons, like secondary and emission, secondary electron emission, X-ray emission, photon emission itself from this incident backscattering, right? When the ion beam bombards the surface of a solid material, then the interaction which happens after this emission, there can be a chemical reaction, there can be heating, there can be even a crystallization change. The atoms which are available over here can change. Okay, so the basic interaction mechanism between the ion beam and the solid material should be there first. And then the B part, the ion, small particle of ions displaces the electrons, as you can see here, and the atoms loses the electron. In the C, in the C part, the lot of ions come, like instead of one there are now n number of ions, and this is called sputtered particles. Now it is not anymore ion, it is now sputtered particles because it is very in close proximity. Then this is called etching because now it has created a cavity over here. There was no cavity in this picture A now, and there is a cavity in picture C. Then D, there can be some thermal effect, that if it is able to, some phase change is there, crystallization is changed there, then they, because of the thermal effect over here, irradiation which we call. E, the gas injection is there too, if you want some particular proper structure, like you want to you want some like these arrays like structure, if you want very smaller cube like square like structure, sphere like structure, then we need some external force to arrange those atoms in that form. So here the gas injection system, like gases are used, like xenon, like helium, like gallium. The gaseous form of these elements are used, and it is to able to implantation and then perform the lithography. Lithography is nothing, it's just a technology to deposit the material at nano level. So in this way the fib works, and we are able to write and even read it, because we have to deposit also. No, first we have create the cavity to write, and just to read we have to fill the gaps. Anyone has a question still now? Any questions still now? So we will move on to our next question. Numericals. Okay. Problems on surface to volume ratio. Problem, the nanomaterial works differently because the surface to volume ratio is very high. Sometimes we have a nanomaterial, suppose of 10 nanometer. It is a nanometer. Sometimes we have a surface which has 10 which has a dimension of 10 nanometer, and it gives 70% surface to volume ratio. And we have a surface of size of 2 nanometer, in it has 84% of surface to volume ratio. Which will give better electrochemical property or catalytic property? Anyone? This will give better property, and since the surface to volume ratio is very low, so okay, wait, so this will not be considered a good nanomaterial or even a nanomaterial, because the one of the characteristic of nanomaterial should be high surface to volume ratio. So it is just like a perception that it is a nanomaterial, but it's not showing properties like nanomaterial. uh, One student has asked a question, that Manomani, this is a doubt discussion class. Okay, if you want to see the video lectures, then you need to go on swam, and then the lectures are available. Here, this session, the Friday session, is the summary session as well as problem solving session. If you want to see, if you want to see the lectures which are uploaded, then you have to go on NPTEL or SWAYAM. Okay, Manumani, I think I'm clear. The course has been started on 25th July. So there are video lectures. So you have to study those first. Uh, Numericals. In your assignment, there were different type of numericals. So here we will practice some of the questions. Question 1. How many nanotetrahedrons can be packed into 1 meter cube? Suppose the dimension of each tetrahedron is 10 nanometer. Can anybody solve these questions, or can anybody tell the approach to solve such questions? If not, do you know what is a tetrahedron first? Are you familiar with this word, tetrahedron? It is in shape like this. Wait. My pen is not working, so kindly bear with me. It is like this. Yeah. Are you familiar with the shape, Kiran? It's okay. So, what is to solve this type of question? We need to divide. I don't know why my pen is not working. Just give me a minute to solve. Just wait a minute. Okay, we have to uh, like you have to see how does it work. The volume wait, I'm dictating the answer. If you can follow me, then you can write. We can solve this question verbally also. So the question is, how many nanotetrahedrons can be packed into 1 meter cube? So tetrahedron is the shape like this, which I have drawn here. The volume, the formula for a tetrahedron is 1 by 3 into area of the base into height. So this is the base over here, okay, and this is the height. Area of the base is 10 into 10 nanometer, okay, and the height is equal to the root 6 divided by 3 into 10. The height of the tetrahedron is root 6 by 3 root 6 by 3 into a 10 into 10. So the volume which will be coming out will be, it will be equal to, what is root 6? What is under root 6? Answer in the chat box. Give me the value of root 6. 2.45. Yes. Then divided by 3 into 10. So the volumes comes out to be 272.2 nanometer. This is the volume of one nanotetrahedron. But we have to find number in the 1 meter cube. So to find the number, we will divide 1 meter cube by 272 nanometer cube. Using the calculation, you have to first convert meter cube into nanometer. So it should be 10 raised to power 9 3 times. You have to multiply it 3 times and divide 272.2 by divided by uh, nanometer cube. So your answer will be, what will be your answer? The answer will be the number of nanotetrahedron is there. I have explained you the calculation and you will give me the answer in the next class. Now moving on to the second question. I apologize that my pen is not working at all now. Next question, you can write, how many C60 would it take to fill a 10 micrometer long single wall carbon nanotube of 1.5 nanometer diameter? You should write this question. My pen is not working, you have to write this question. I am repeating it once again. How many C60 would it take to fill 10 micrometer long single wall carbon nanotube of 1.5 nanometer diameter? You have to solve this question like this only, like the previous question which we have done in question 1. You have to take out the volume of 10 micrometer. You have to take out the volume of 10 micrometer. Then, sorry, not volume, the area. Area will be pi into r square. R square is, you have to find a cross section area, half of the 10 micrometer, and then the area of the single wall carbon nanotube, that is 1.5 nanometer. You have to again put the formula pi r square and divide both the numbers and you will get the correct number of C60 available. So this question is same based on the similar fact. Okay. Now next question. Assuming, next question. Assuming van der Waal radii, how many hydrogen atoms can be squeezed into the length of 1 nanometer? You have to find out how many hydrogen atoms can be there in the length of 1 nanometer. Repeating it again, assuming van der Waal radii, How many hydrogen atoms can be squeezed into length of 1 nanometer? The numbers which you will be requiring, the radii, to find out the radii of the hydrogen bond is 1 angstrom. 1 angstrom means 0.1 nanometer. Solve this question and I will check my pen if it works. I am giving you 2 minutes to solve this question. हेलो हेलो हरी ब्रह्मा, ये पेन चल चलते ना वो हो गया, मतलब स्मूथ नहीं चल रहा। हाँ, एक बार तुम नीचे आना है नारफ में। Do I need to repeat the question again? No, answer should is not, it is not one. Answer is not one. The radii which you have to take is 0.1 nanometer. You have to find out the area. ये कैसे चलते हैं, जैसे डॉट डॉट आने लग गए। बैटरी कम है क्या? डिस्चार्ज हो गई। लैपटॉप से लगानी पड़ेगी चार्जर। तो फोन से तो मैं लगा लूंगी, ये रहा मेरा फोन, फोन से मैं लगा लूंगी, कोई बात नहीं। मुझे लगा मैं इतनी जोर से बात नहीं कर रही।
ये लाइट चलनी बंद हो गई ना।
हाँ, कम कम चल रही थी।
एक मिनट, ये चार्ज नहीं हो रहा आपके फोन से।
नहीं, वो अलाउ करना पड़ता है ना चाहे।
ठीक है, इसमें
चलो ठीक है, अभी दे दूंगी थोड़ी देर में।
देखिए चल रहा है, ऐसे नहीं काम करेगा। वही चल,
हाँ कर। Okay, so my pen is working now. I will write the question. I will write the question on the board. Question number 2. How many C60 would it take to fill 10 micrometer long single walled carbon nanotube of 0.5 nanometer? Fine. This question will be solved as this only. The volume, if you have not written volume of tetrahedron, is 1 by 3 into area of the base into height. This is height and this is the base. So base is 10 into 10 nanometer, and height, to calculate height, the dependency on the dimension of the tetrahedron is root 6 by 3 into a. and A is equal to 10 over here. You will find the volume. You know the volume of your 1 micrometer cube, and you will get the answer. Okay. Yes. Now the second question. Now the third question I'm writing. I'm writing it over here. If you have not written or solve it, as you have to assume how many hydrogen atoms can be squeezed into the length of 1 nanometer. This is the length only. You have to consider 1 nanometer. What is the van der Waal radius? This is the van der Waal radius. Which I have told you to be 1.1 nanometer. 1 Armstrong is equal to 0.1 nanometer, and sorry, my mistake. The van der Waal radius is 0.24 nanometer. I was giving you the conversion. Okay, so the van der Waal radius is 0.24 nanometer. So 1 divided by 0.4 nanometer. Around 4.8. So answer is around 4 atoms. 4 hydrogen atoms can be squeezed into 1 nanometer length. Okay. So these are the problem solving which we are doing today. And the last question for the today is based on this wavelength spectrum. The last question is based on the wavelength spectrum. I hope you are aware of this wavelength spectrum. How many of you understand this wavelength spectrum? You can write your reply in the chat box. If you're aware of the wavelength spectrum, then you are able to solve the next question. If you're not aware, I will explain this over here to you. So I need your response. Okay, Shashwat is saying yes. Other students? Okay, so we have got couple of responses. Now moving on to my next question. Okay, fine. I will explain once. So wavelength spectrum has the information about all the, okay, I'm explaining, has all the information about the types of radiation available in the universe. Whatever the be it radio waves, be it microwaves, be it gamma rays, everything have been articulated into this chart. So the radio waves range from 10.1, this is in the meters. It is, remember, this chart keep on changing when the wavelength, unit of wavelength changes. There will be different numbers if it is in nanometer. If it is an Armstrong, these number will be different. So you have to first see your wavelength spectrum, the unit of your wavelength spectrum. It is in meters, right? So the radio waves, which is used in the radios and for the communication for the satellite purposes, it uses radio waves and fall into the range of 10 raised to 0 to 10 raised to power 1. That means the wavelength is long. They are long wavelengths. And I have explained uh, this concept that why was there is need of electron microscope, because we need to see smaller things, so we need smaller wavelength. If we want to see larger things, then we need larger wavelength. So radio wave travels very long distances, so we need wavelength of long range. So that is why radio waves fall into this category. Now it will get decreased as we move on to the left hand side. Microwave, it falls into the 10 raised power 0 to from to 10 raised power minus 3. Okay, meter. Microwaves, the microwaves which we use to cook food in microwave or ovens, it radiates microwave. Microwave have the ability to rotate, to vibrate the molecules. That is why our food gets heated. Even if your food has a smaller amount of moisture, it will it will give vibrations to those water molecules, and that water molecule will generate heat. That heat will get transferred to your food, and your food will get hot. Your food will get warm in the microwave oven. So this how these it is very amazing to see how these wavelength spectra works in our day-to-day life. Infrared, 10 raised to minus 3 to 10 raised to power minus 6. So you are saying, did you see the concept that radio travels lot? And when we go on to microwave, we have come down to the molecular level. Water molecules, disturbing the vibration of water molecules. So from the larger distances like miles, we have covered the molecules. Similarly, infrared radiation, which are very harmful for us, it is follow into 10 raised to power minus 6 to 10 raised to power minus 3. These are UV and infrared are able to damage our skin cells. They're able to penetrate into our skin and cause diseases. So can you see now it has gone to a much more atomistic level, to a cell level. From the bulk of water molecule, it has now come down to our biological cells. Now from now we get to X-rays. 10 raised to power minus 10, it moves around 10 raised to power minus 9 to 10 raised to power 10 or 11. X-rays. If you want to take X-ray of our bone, I told you, no, there are nanomaterials, 300 nanometer long, 1.5 nanometer thick, 1.5 nanometer thick. To study your bone, we need a source which has wavelength of this much this much length, 1.5 nanometers. So we need X-rays. Then gamma rays, to study the nucleus of the atom. The gamma rays are derived from from the collision of nucleus. So nucleus is too small. It is inside the atoms. It is so densely packed. Stronger and smaller. As we move on to left to right, the wavelength is becoming lower and stronger. As you can see, the frequency is increased from 10 raised to power 8 to 10 raised to power 20 hertz. It has become so powerful. So this is the wavelength spectrum. Now between this hole, a small region which lies is our visible region, which makes which makes our thing visible to us. All these radiation are colorless. Only this smaller region has colors to it, and that is what we are able to see through our eyes, which lies between, if we convert these number, because the number is very small now, it is lying between 10 raised to power minus 6 to 10 raised to power minus 7 nanometer. sorry, meter. So to convert this number to uh, 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 to a to logical and uh, considerable number, I'm giving you the numbers in nanometers, 700 to 400 nanometer. The red lights are red because it can travel longer. It is fall in the longer range of this visible spectrum, 700, and this 400. That is why we see the sky is blue, because it scatters shorter wavelengths. It scatters the light of shorter wavelength. Now my questions are, I will write over here only in this region. You have to predict, if I want to study these things through radiation, listen to my question properly. If I want to study the objects which I'm going to tell you, which radiation we will be using, right? If I want to study the structure of airplane, then which then which waves I will use from the wavelength spectrum? Tell me. No, not X-ray. X-ray has a very smaller wavelength. Huh? See, X-ray has very smaller wavelength. So it will help us to study smaller things. Radio waves, right? If you want, radio waves lies on the larger wavelength. Larger structure, larger wavelength. Okay? So airplane we will use radio waves. If you want to study a bacteria, paramecium. If I want to study a bacteria, no, not gamma. Gamma is the size of a gamma. You can see the wavelength of gamma is as equal to the size of a nucleus. You can see bacteria right now in light microscope. You can see bacteria. So think like that. Yeah, IR. Yes, right. The concept over is, larger the structure, larger the wavelength you need to larger wavelength of radiation you need. Yes, IR. Infrared. IR means infrared. Gold clusters. Suppose it is around 5 nanometer. Which wavelength? This is the last question. So, right. X-rays. Correct. If I want to study um, whole body of a human, whole body, like his his or her height is in meters. The height of a human. Which wavelength we will use? We will use, obviously, radio wave, not X-rays, not like the whole body, not cells. Not cells. We have to study the body, like height. Yeah, radio waves. Chemical bonds. Chemical bonds. If you want to study the chemical bond, is there existence of a chemical bond or not? Chemical bond, answer is microwave. Sorry. Yeah, UV. No, UV will be much smaller. It will give you it UV will give you the information about the energy levels. Okay, from which energy levels are getting excited. To study the chemical To study the presence of a chemical bond, you need microwaves. Similarly, if you want to study the vibration and rotation of water molecules, then you will study microwaves. I told you, no, microwaves helps in keep boiling the water and then our food gets hot. Microwaves. Last question, crystal planes. Crystal planes. I was telling you about 001, 100. If you want to study these planes, then which wavelength I will go for? These are atomistic levels. So tell me. Yeah, correct, Sanjoy. X-rays. Fine. So I hope the class was very useful to you all. If you have any doubts, you can ask me, or otherwise we will finish the class. If you have any doubts, you can raise your hands. Okay. Thank you. Thank you, class.